Good morning. Happy Tuesday. Okay, so I got you guys to watch an introduction to hypothesis testing. Now, hypothesis testing is a lot of steps. There's a lot of methodology to remember. And so we're just going to break it down and talk about each individual step with this example that we've introduced. And so I'm going to recap a lot of what you learned in the Friday video, but that's probably a good thing because it's the hardest part. And what we talked about was setting up your null and alternative hypotheses. And that is the hardest part of these questions. Now, we are starting with hypothesis testing using confidence intervals, whereas later the more formal version and the version that we will use eventually is using p-values. So I'm going to introduce them side by side. And that can be a little bit confusing, but it's good to see that link right away. So it feels like a lot, and it is a lot, but we'll just keep working at it. Okay, so one of the things that I would encourage you to do is the first thing I do, at least, I don't know, maybe you want to do it, maybe you don't, is to identify what type of question we have. Okay, so we've only seen this one type of problem so far, right? But we could break it down into, we have a binomial problem, or we have a z-score problem, or something like that. But especially for confidence intervals and hypothesis testing, it's going to make it a lot easier if you know what type of problem you have. Okay, so the first thing we're going to do is we're going to read through this example, just kind of refresh what it is. Then we're going to talk about what type of question it is and why. Okay, so according to a 2012 Bank of Montreal RRSP study of 1,000 Canadians 18 years of age or older, 67% of Canadians have an RRSP. Okay. A StatsCan study reported that in 1999, 57% of Canadians had an RRSP. And then I created the question, is there evidence that the proportion of Canadian adults who have an RRSP has changed since 1999? Okay, so that's the question that we want to solve. And what we finished off with on Friday was we just identified some of the key information here. So we have a sample size of 1,000. So one thing I want you to notice is there's only one sample size, which means you only have one sample. Okay, and so let's first talk about the type of question. We start with whether it's one sample, or eventually it's going to be two samples, or potentially more than two, but usually we just have two. Okay, so two samples. One sample in this case. So this is a one sample, and the parameter that we're interested in is the proportion, right? So these percentages, 67%, 57%, those are all proportions because percentages are proportions if we divide them by 100. So this is going to be a proportion question, right? So it's a one sample proportion question. That's going to help guide us through how do we solve these problems. Okay, so just knowing that it's a one sample proportion question tells us how to solve the problem. Okay, we don't know how yet because we haven't really solved it yet, but we will. Okay, so if any one sample proportion question will follow the same steps. Okay. So, all right. So I've got a sample proportion I've got a sample size, and I've also got a proportion that I want to compare my sample proportion to. Okay, and so that's what makes this your null value or your hypothesized value. Okay, so P naught is the null value or the hypothesized value. Usually I'll call it the null value because it's a little bit shorter to write. But this is the value that we want to compare our sample proportion to. In fact, we want to know if there's been a change, right? So we're not specifying whether it's lower or higher, right? Even though, I mean, 67%, you could only use it to prove that it's higher. But there's a reason that we're talking about the change, which would be either lower or higher. And that's kind of more useful to us. Okay. So the value that we want to compare our sample proportion to is the 0.57. Okay. So that's the value that we're going to talk about in our hypothesis, or hypotheses rather. Okay. So one thing that I want to mention before we kind of get carried away here is there's two ways that we could ask this problem, right? So the other way would be very similar, right? We take a sample of 1,000, and then instead of giving you the proportion, the sample proportion, I might give you the number of successes, right? And so this question gives us n and p hat. Okay. So n is equal to 1,000 and p hat is 0.67. Okay. But another way we could ask this question, another way of asking this question is by giving what, n and x, where x is the number of successes, where x is the number of successes, right, or the counts. Okay, so that would make n is still 1,000, of course, so that's going to be given regardless. But then the x would be the number of successes. So it might say 670 of those Canadians, right? So just kind of gonna steal this here. Whoops. Copy. All right, so what that would look like. Sorry, it's all marked up, but that's okay. So instead of 67%, it might say 670 of those Canadians have an RRSP, right? So that's the other way that we could word this, but you'll notice later it's going to be easy to pick out the proportion questions, mostly because they don't have a mean and they don't have a standard deviation, right? That would have to be included in the problem. But for now, right, it can either be the counts and the sample size, or it can be the sample proportion and the sample size. Okay. Either way, you've got a one sample proportion question. Okay, so we've identified the sample size, we've identified the null value, so the value that I want to compare my sample proportion to, right? And I also have my sample proportion, and we've identified the population, right? So this is the population that we will be able to talk about in our conclusion. Okay. So let's see here. We want to know if there's been a change since 1999. So let's do a quick recap of the steps, the general steps for hypothesis testing. Now, usually I abbreviate hypothesis testing just to HT because it's really annoying to write, right? So just HT is fine. I break it up into 4 steps, but I mean, depending on what textbook or kind of what field you're in, they might break it up into 7 steps or something crazy like that, where they kind of talk about, okay, you set up your null hypothesis, then the second step is setting up your alternative hypothesis. I've lumped that into one, and then so on and so forth. So, but in general, we're all going to do the same things. I just feel like 4 steps is a nice number to kind of guide our analyses. Okay, so we do the same stuff, so don't be thrown off by more or potentially less steps, but usually not less than 4. Okay, so the first step you're going to do is, well, the 0th step is going to be checking your conditions. We've kind of ignored that for now because there's so much that we have to introduce here. And so we're kind of parking lotting the conditions for a little bit and just focusing on the hypothesis testing itself. But you would have to check the conditions first. But you know how to do that, right? The normal assumptions for the proportions. Okay, so first step is to state the hypotheses. Now, a lot of these steps aren't really going to make sense because we haven't seen them yet, right? But we kind of, I like to just introduce the entire flow and then we'll fill it in as we go. Okay, so first step, we're going to state the hypotheses, and then we're going to come back and we're going to actually talk about exactly how that works in this question. The second step, I usually call it do the test. But that's kind of, it's really vague actually. But I'm still going to call it that. So do the test. And if you're using the confidence interval approach, then it means calculate the confidence interval. Or if you're using the p-value approach, which is the more formal approach, which we'll introduce later, then it's calculate the test statistic. Okay, so do the test refers to the test statistic, but for now it just means calculate the confidence interval. Okay. The third step is going to be it's usually find the p-value, but because we're opening ourselves up to either the confidence interval approach or the p-value approach, I'm going to call it gather evidence. So gather evidence. In the confidence interval approach, there's not a lot that we're going to do here. It's going to be compare the confidence interval to the null value. Compare the confidence interval to the null value. Or in the p-value approach, it's find the p-value. Okay. And then your fourth step is your conclusion. Now your conclusion has multiple parts. It has 3 parts. I break it up into 3 parts. But I'll just leave it there. Okay, so remembering our goal of hypothesis testing is I have this idea about how I think or hypothesize that the population behaves. Okay, and so in this case, we want to know, has there been a change in the proportion of Canadian adults who have an RRSP since 1999? Okay, so then what did we do? We collected a sample from 2012 and we found a sample proportion. Now we're going to use that sample proportion to try to gather evidence either for or against that the null hypothesis, which is going to be that there's been no change. Okay. So I'll call this the end of our review. It's the end of the page too, so that's why it's all kind of crammed. But here, let's go into more detail about stating the hypotheses in terms of this question. So step one is to state the hypotheses, and maybe I won't do this one. I'll just call it step one. State the hypotheses. Pop this over here just a little bit more. Highlight it a little bit. Okay. So your hypotheses in this case, well, in any case, will always look the same. Okay, it depends on the question that you have, but the general setup is going to be the same. So the first thing I want you to do, even if you're not sure of what your hypotheses are, I want you to start with an H naught, and then below it an HA or an H1, depends on what you prefer. And maybe I'll make this 0 but they are subscripts, so they should be kind of down low. Okay. So you're going to start with a null hypothesis and your alternative hypothesis. Okay, the null hypothesis is always going to be the statement of no change. Okay, so this has to be, so H naught must be a statement of no change. Okay. And these are both statements. The null hypothesis is a statement and the alternative hypothesis is a statement. And so what you have to do is you have to follow these statements with colons. Okay. One common mistake that I see here is you put equal signs, but equal signs in math fields are numerical equalities, right? And so, or equal statements, which is not what we're doing here. So it's really important that you have these colons here to indicate that it's a statement. Okay. Now, even if you're completely lost, okay, then the null hypothesis has to be a statement of no change. Okay, which means that there must be an equal sign in the null hypothesis, right? So a statement of no change means that we have to have that equal sign in there. Now, our hypotheses are always going to be about the parameter, okay? The parameter that we're interested in. So depending on the question type, okay, which here we decided we have one sample proportion. So then the parameter that we're interested in is going to be the population proportion P. Okay, so the parameter of interest depends on what type of question you have. Okay. And if you have a look at the formula sheet that I posted, it's outdated in the sense that it's the sections are all weird because they changed the textbook completely, and so the numbering won't help. But because you're making your own formula sheet, it doesn't really matter to me. But you will have to go and scroll down, and it's the 121, 124 sheet, but it's the same. So we just go a little bit deeper. But what I've done is I've set your default null and alternative hypotheses, right? And that's going to be the case for all of these different question types that we will go through. But we're actually starting with the one sample proportion question type. Okay. So there's a big box here, and I'm going to bring it up in. And oh yeah, like I was saying, so you're making your own formula sheet. So this is really just as a guide. It's not going to be a great formula sheet on its own, but you can use it to figure out what things I would have given you on a formula sheet. Okay. Now, so we've decided that this is a one sample proportion type of question. We already decided that. Okay. So our hypothesis test is going to be for P, the population proportion. Right? So P is the population proportion. Oops. The population proportion. Okay. So that means our hypotheses will be about P, and it's going to be comparing the population proportion to some hypothesized proportion, right? So some null value. Okay. So this here, this P naught is the null value, which is the value, P naught is the value we want to compare our sample statistic from, or our statistic to. Remember, statistic means it comes from the sample, so I don't have to say sample because statistic can only be from a sample, right? So P naught is the value we want to compare our statistic to, which means that in this case, for this example, the value that we want to compare our sample proportion to is 0.57, the value from 1999. Remember, we want to know if there's been a change from 1999. Okay, and in 1999, it was 0.57. Okay, and so here, this null value, right, we're going to replace it with a value from the question. So in this case, it's going to be 0.57. Okay, and we already decided our hypothesis will be about P. And so let's see here. For one sample proportion, we're hypothesizing about P. Okay. So it takes a lot of work to set up your null and alternative hypotheses, but it's worth putting in the work because everything that you do afterwards will just kind of flow from here. Okay, and so your null hypothesis always has an equal sign. It's going to be about some parameter, right? So some population thing, right? It can be a proportion or it can be a mean, typically. And then the null value in this case for a one sample proportion type question, it's going to be the value you want to compare your statistic to. Now, you don't want to say something like, oh, I'm going to test the null hypothesis that there's been no change from 0.57, and then your conclusion is about something else, right? Of course, your alternative hypothesis just has to be an alternative of the null hypothesis, right? So whatever you have here, this P is going to get transferred down. So your alternative hypothesis has to be about the same thing, right? And so here you've got your P, and of course, how does it compare to 0.57? The only thing that changes in your alternative hypothesis is the sign, or the inequality rather. Okay. So those just kind of transfer down, and then your alternative hypothesis, because we want to know if there's been a change, then we have not equal to here. Right? If there's been a change, then P is not equal to 0.57. So here, the word change means it's not equal to. If we had less than, it would be less than. If it's greater than, then it would be greater than. But for using the confidence interval, we can only detect a change, the not equal to, right? Because remember, an interval goes in both directions, right? So for confidence intervals, we can only test for a change using confidence intervals. Or maybe I should reword that. If using confidence intervals, we can only test for a change. Right? Otherwise, what I was saying was that you can't test for a change unless you use a confidence interval, but that's not true. Right, so the restriction is on using the confidence interval. Well, then you can only talk about has there been a change, which is what we want to test. So, so that's exactly what we want. Okay. So here, for the hypotheses, we built this up and we kind of wrote all around it. And the main thing that we need to remember throughout all our testing is that we do all our testing assuming the null hypothesis is true. Okay, so we assume that P is 0.57 until we have proof otherwise, right, from the sample. And so here's a note. We do all of our testing assuming H naught is true. Okay. That's going to come back into play later in our conclusion, for example. But it's important to kind of keep that in mind as we go through this. Okay, so we assume that the null hypothesis is true, even if it's not what we're trying to show, right? But the goal is to have our sample have so much evidence against that, right? Saying things like, oh, well, the probability of that happening is so low. If the null hypothesis were true, well, that makes me lean towards the alternative hypothesis, right? So, in summary, this step would just look like this, right? The null hypothesis is a statement, the alternative hypothesis is a statement, and P is equal to 0.57, or P is not equal to 0.57, right? So this is what this step would look like, right? You don't have to include anything else, but I just wanted to talk around it. Okay, so that's your first step. Okay, I would argue it's the hardest step because you have to figure out what type of question you have and figure out what your null and alternative hypotheses are. So this is a big step. Okay. Second step, so step 2, is to do the test, which depending on what approach we're using, right? If I'm using the confidence interval approach, oops. That means calculate the confidence interval. Calculate the confidence interval. Okay. Whereas if we're using the p-value approach, it means calculate the test statistic. Now, we're not going to do this one, but I think it's helpful to see that it's actually given to you on your formula sheet, right? So the formal hypothesis testing procedure involves setting up your null and alternative hypothesis, which we do, but then we're going to skip down to calculating the confidence interval, which we already know how to do, right? Whereas later, what we're going to do, and I drew over it, so there, is calculate this z-score, which is a test statistic. Okay, and so here it kind of outlines how you would do it. And then once you have a z-score, what can you do with a z-score? You can use the z-table if you wanted to, or R or Excel to find probabilities, right? You could find areas under the curve. Okay, so that's nice, and we will leverage that eventually. So the p-value approach, we would have to calculate the test statistic, such as Z, okay, or T later on. But there's lots of test statistics that we could consider, right? We could consider or T or F or chi-squared, right? There are lots of different test statistics, but for now we only know Z, but we're going to introduce all these other ones as well, right? So we will see these, and this is the step where we would calculate those test statistics. Okay, so just beware. We're going to have different ones here later, right? But notice that the formula sheet tells you which one to do, right? So in our case, it tells us to calculate a Z. Okay. So in this example, I'm doing the confidence interval approach. And so we're using the confidence interval approach for this example. Okay. And the default confidence interval that we're going to calculate is a 95% confidence interval. And so the default CI, or I guess confidence level is what it's called. Default confidence level is 95%, right? I don't think it said use a confidence interval because we could do the p-value approach as well. But the default confidence level is 95%. Okay, and so let's calculate a 95% confidence interval for the proportion, the population proportion. Okay, so we calculate a 95% confidence interval by, and notice that the confidence interval equation is on your formula sheet, right? Or just have it jotted down somewhere, that's fine. And all we really need is the p hat, which means that we have n in some capacity, right? And the only new thing that we need to introduce is the z star. Z star, remember, is the critical value, which determines the width of your interval, right? So p hat plus minus the margin of error. Now the margin of error is z star times p hat q hat over n. I'll clean up that q hat. We know a lot of these components, right? 0.67. So p hat is 0.67. P hat is 0.67, which means q hat is what? Maybe I should use a different color here. Q hat is 1 minus p hat, which is 1 minus 0.67, which I think is 0.33. I'll just confirm. You don't want to be a hero and do it all with the wrong number. It is 0.33. Good. And then finally our n is 1000. And the one thing that we don't have yet, z star, is the critical value. for a 95% confidence interval. Okay. How do we find it? Well, we can go to our t-table, and I actually made a shortened version of it here because we ignore everything. So I'm going to copy that in, but remember it's from this t distribution table. And so I call it the t-table or table C if you prefer, but that's kind of specific to this set of tables. It still works. We need to give it the confidence level, and then we can go all the way to the bottom and find the appropriate Z star. So I'm going to copy this table in. Okay, so we've got our confidence level and we've got our Z star row, and for 95% confidence interval, oh, helps if I don't draw over it. We see that Z star needs to be 1.960. You might have that memorized, maybe not. Back in my day, we had to memorize these. Well, not the lower ones, probably starting at 90%, right? There's some key confidence intervals that we build, but I want to give it to you. So there you have it. Okay. So Z star is the only thing that dictates the confidence level, right? And that's really all it's doing. Okay. And so this whole chunk, remember, we call it the margin of error, right? This is the standard error, and this whole thing is the margin of error. Okay. I'll clarify that once we, why did we do 95%? Because it didn't say, and the default confidence level is going to be 95%. So if you're ever unsure, then use a 95% confidence interval. Good. So let's plug in our values and see what our confidence interval is. So we have p hat plus minus Z star times the square root of p hat q hat over n. So we've got 0.67 plus minus 1.960 times the square root of 0.67 times 0.33 divided by 1,000. Now, when you're doing these calculations, main thing, don't forget the square root. But you'll want to be methodical, right? So 0.67 times 0.33 divided by 1,000, then square rooted. I'm going to jot down that value so I don't write out the values in between, because it's just a lot of writing and it's easier to just do it on your calculator. But I will jot down what the standard error is. Okay, and so here we get to 0.67 plus minus 1.960 times 0.67 times 0.33 divided by 1,000, and then take the square root of that, puts me at 0.01486943173. Now you don't want to round any values here. It's important that you keep all your decimal places until the very end. Of course, there are likely more decimal places beyond this, but my calculator won't show them. So it's a good idea to store that value, or in my case, I'm just going to multiply it by 1.96 and then store that value. So this square root here is the standard error. So this is the standard error of p hat. Okay. So usually questions might hold your hand through the calculations, and maybe you already have the standard error of p hat, right? So then you can just plug that in, but in general, we won't. And then 0.67 plus minus, and then I'm going to multiply that by 1.96, and I get 0.02914408,619. Now this is the margin of error. Right. Once I've multiplied by the confidence level, then I have my margin of error, right? And notice that that's kind of the buffer around our sample proportion, 0.67, right? Because we understand if we took a completely different sample, then my sample proportion wouldn't be 0.67. I expect it to be around there, right? But we're building this buffer or this interval to try to figure out what it might reasonably be. How do we write our confidence interval? Well, we're going to write with interval notation, right? And so my round bracket, then my lower value, comma, my upper value, and then another round bracket, right? And so here I get, I'm going to store the margin of error in my calculator. Now, you might have to figure out how your calculator stores value, but most calculators will store values. Oh yeah, so the standard error is just the standard error of p hat. So that's the spread of p hat, whereas the margin of error takes into account the confidence level as well. So this, everything that including the square root is the standard error of p hat, and then we found the whole plus minus chunk is the margin of error. Okay, so my confidence interval, once I've stored the margin of error, I get 0.67 minus that stored value. I'm going to write out the whole number, and then I'm going to I'll round it probably to 4 decimal places. So I get 0.6408559138 up to 0.67 plus that stored value, which is 0.69914400862. You're going to follow the rounding instructions that are in the question, but if there are no rounding instructions, then 4 decimal places is usually safe. And so let's round to 4 decimal places. Round to 4 decimal places. Then I get 0.6409 up to 0.6991. In a hypothesis testing question, we don't typically interpret the interval, but just for practice, let's interpret this interval, right? And so we don't need to interpret the interval. In a hypothesis testing question, but let's interpret this interval for practice. Okay. We built a 95% confidence interval, so we are 95% confident right? That's where we start. That the interval from 0.6409 to 0.6991, right, captures the population proportion of adults who have an RRSP when? In 2012, right? Because that's our population. So we're 95% confident the interval from 0.6409 to 0.6991 captures the population proportion of Canadian adults who have an RRSP in 2012. So this is the population. This is the parameter that we're interested in. This here is the lower value of your confidence interval, and this is going to be your upper value. Right, so it's got that, and this is the default 95% confidence interval that we built. Okay, so the interpretation of your confidence interval is always the same. We are some percentage confident that the interval from here to here captures this parameter, right? Whatever you're interested in, and then of what population. Okay, so let's see here. Good. Okay, so we did step 2. In fact, I'm going to underline it like I did step 1. Okay, and so now I have a confidence interval. Good. So now, and I don't need to interpret it. It doesn't hurt to interpret it, right? But now we're ready for step 3, which if we're using a confidence interval, we don't really do much in this step, right? But I'll show you what I find helpful. Step 3, I'm going to call it gather evidence. And that's because it depends on if we're doing a confidence interval approach or the p-value approach. Okay. I'll underline it in pink before I forget. So in terms of the confidence interval approach, you're going to compare the confidence interval to the null value. Okay, so compare the confidence interval to the null value. For the p-value approach, it's going to be find the p-value. That's very vague, and we're not going to get into it. We're going to save that for later, right? But we're going to say find the p-value. Save this for later. Okay, next day. Okay. So we're not going to do that, but that's what we would do, and I'll show you how to do it. Okay, but for now, right, in this example, we're using the confidence interval approach. So what I like to do is I like to draw a number line that includes my null value and my confidence interval. And then what I'll be able to see is I'll be able to visualize whether my null value is inside the interval or not. Okay, and so here I draw this number line here, and I know my confidence interval goes from 0.6409 to 0.699. So 0.6409 to 0.6991. Notice that I'm just drawing this interval, right? I'm just kind of figuring out, just showing, so there's no ticks or anything. I'm just kind of showing, okay, here is the interval from 0.6409 to 0.6991. Now what I want to do is I want to put my hypothesized value, my null value. So here, compare the confidence interval, which was 0.6409 up to 0.6991. And I want to compare it to the null value. P naught was 0.57. So now I'm going to put 0.57. And the only thing that I'm looking for is it in the interval or not? Right, 0.57 is somewhere out here. Right, it's a number line, so it's increasing as we move through. And what we see here is the null value is not in the interval, right? So we can kind of skip this step because you can look at 0.57 and see if it's in the interval, and then you can use that in your conclusion. But I find that it's useful to kind of convince myself by putting them on a number line. Right. I will say that this step is optional using the confidence interval approach, because we're going to reiterate it as part of our conclusion, but it's okay. Okay. So step 4 is our conclusion. Okay. For the confidence interval approach, I'm going to highlight what the steps are, and then I'll do it for the p-value approach. But that's not going to make any sense because we don't have a p-value to look at quite yet, right? But I just want you to have seen it once, and then we'll see it again. We'll introduce it over and over again. But so in the confidence interval approach, maybe I should have it set up the same way that I did before. So I can do a confidence interval approach, or I can have the p-value approach. Either way, the conclusion is going to have 3 parts. Okay. The conclusion will have 3 parts. Okay. So for the confidence interval approach, the first part is to compare the p-value to the, compare your interval to the null value, right? Which is what we did here, right? Compare the confidence interval to the null value, but here you're going to say it, right? State the comparison between the confidence interval and the null value. State the comparison, or state how the CI compares to the null value, right? Is it in the interval or not? Okay. Your second step is to say, what does that mean in terms of the null hypothesis? So it's going to be your conclusion in terms of H naught. Okay. And we're going to fill in the gaps here, but I just want to show you the confidence interval approach versus the p-value approach, and then we're going to focus on just the confidence interval approach for now. So the conclusion in terms of the null hypothesis, And then finally, the conclusion in terms of the question. Now, people love to forget about that one because there's so many steps that you have to do. It's such a big question that you're solving. And then when it comes down to your conclusion, you feel like, there, I did it all, I said it all. And then you forget to do the conclusion in terms of the question. Okay, and so that's going to be really important. Conclusion in terms of the question. Right? Don't forget this one. Right? Because that's the one people easily forget. Right? Now, for the p-value approach, instead of stating how the confidence interval compares to the null value, we're going to compare the p-value. So state how the p-value compares to the alpha level. Okay. That doesn't mean anything to you right now, but it's nice to have them side by side, right? So here, notice how kind of similar they are, right? In the wording at least. So you're going to compare something to something else, okay? Something to something to something. Your second step is going to be the same though. So based on the comparison from step one, then you're going to be able to draw a conclusion in terms of H naught. So then it's going to be your conclusion in terms, of H naught. And finally, it's going to be the conclusion in terms of the question. Right, and so notice that these last two steps are the same steps, regardless of how you did your hypothesis test. Yeah. So in our example, right, our conclusion and make it dark. Our conclusion is going to look like this. So if we've built a confidence interval for the proportion of Canadian adults who have an RRSP in 2012, and we find that it's between 0.6409 and 0.6991, then are you going to feel comfortable saying that there hasn't been a change since 1999 when the population proportion was 0.57? No, right? This looks like there has been a change. It looks like it's increased, but we haven't tested that because a confidence interval can only tell us if there's been a change. Okay, so it looks to us because 0.57, so because the null value is not in the interval, right, then what we're going to say is we have enough evidence to reject H naught. Okay, so since the 95% confidence interval from 0.6409, I want to say, or yeah, 0.6409 to 0.6991. Okay, I always like to emphasize things using the values that I've calculated, right? And that's a good way of checking to make sure that what you're saying makes sense as well. So since the 95% confidence interval from 0.6409 to 0.6991 does not contain the null value, of 0.57, okay, we have enough evidence to reject H naught, right? We have enough evidence to reject H naught. And if we're going to reject H naught, which says that the proportion has not changed, then you should probably say in favor of what? In favor of it having changed. So we have enough evidence to reject H naught in favor of HA. This doesn't mean anything. So if you're reporting to your boss, they don't care about this statement, right? The only thing they care about is, well, has there been a change or not, right? So you work at the bank and you've run this analysis, and has there been a change or not? So you have to answer the question. And so what does this mean, right? This means there has been a change, or what I prefer to do is I just like to take the question and reword it as an answer, right? So if we go back to the actual question here, way up top. Oh, here, right? Is there evidence that the proportion of Canadian adults who have an RRSP has changed since 1999? Okay. Rewording this as an answer, yes, there is evidence that the proportion of Canadian adults who have an RRSP has changed since 1999, right? So it's wordy, but you don't have to come up with any of those words on your own. So you just reword it as an answer, right? So yes. There is evidence that the proportion of Canadian adults who have an RRSP has changed since 1999. I think was the question. Is there evidence that the proportion of Canadian adults who have an RRSP? Yeah, okay. So I just reworded that question as an answer. Okay. So if we kind of use different highlighters here, let's see if I can find different highlighters. So in step 1, state how the confidence interval compares to the null value. Well, that's this portion, right? So I'm comparing the confidence interval to the null value, which I already did just to get an idea of what my conclusion would be in step 3, but here we see it in action. My second step is to draw my conclusion in terms of H naught, right? So if the null value is outside the interval, I have enough evidence to reject H naught. If the null value, which is my null hypothesized value, is in the interval, then I do not have enough evidence to reject H naught. So I'll outline the 2 options here, but my conclusion in terms of H naught is sorry, I'm reading the comment, but I'll read that chat in just a second here. So so we have enough evidence to reject H naught in favor of HA. That's your conclusion in terms of the null hypothesis. There's only 2 options. You either have enough evidence to reject H naught, or you do not have enough evidence to reject H naught. And that's because we do all our testing assuming the null hypothesis is true. No, so now I'm going to the chat. So you have to solve the problem, right? in order to get to this conclusion. But then to play it safe, you can just reword the question as an answer. But you had to do all these steps to figure out what the answer was, right? So you have to solve it. Yeah. Okay. And then finally, oops, let's find a different color here. The conclusion in terms of the question is this part. Okay. And this can just, we can usually reword the question as an answer. So your conclusion can go one of two ways, right? If the null value is inside the interval, okay, so the conclusion in terms of H naught only has two options. Only has two options. If the null value is in the interval, is in the confidence interval, then we do not have enough evidence. We do not have enough evidence to reject H naught. Okay. Or the other option is if the null value is not in the confidence interval, then you have enough evidence to reject H naught. So if the null value is not in the confidence interval, that means that we have enough evidence to reject H naught. Okay, so notice the differences here, right? So if it is in the confidence interval, then we do not have enough evidence to reject H naught. And if it is not in the confidence interval, and maybe I should just highlight, if it is in or is not in, right? So if it is in, we do not have enough evidence. I'll just highlight the key portion, sorry, do not. Then we have enough evidence to reject H naught. And usually we would say in favor of HA. Right? But your conclusion has to be whether you have enough evidence to reject H naught or you don't have enough evidence to reject H naught, because we did all our testing assuming the null hypothesis is true, right? We either have enough evidence to reject H naught or we do not, right? There are no other options since we did all our testing assuming the null hypothesis is true. But there are no other options since we did all our testing assuming H naught was true. Okay. Okay. So that's how you're going to solve these hypothesis testing problems using a confidence interval. And so what I want to do next day is I want to show you how to do it with the p-value approach, which is the more formal testing approach. And it's especially if you're going to go on in academia, so you're publishing research papers and stuff like that, then you would have to use the p-value approach. But there is some kind of talk in the academic community that maybe we should be moving towards confidence intervals, but it does have some drawbacks. But I want to start with that next day. So I think this is a good place to stop for today. And a little bit early, but usually people aren't too upset about that. If you have any questions, let me know. Otherwise, I will see you on Thursday. Okay, I'll stop this recording here.